Time travel, an idea so captivating, it has sparked imaginations for centuries. Whether in the pages of science fiction novels or in the vast reaches of scientific theory, the concept of stepping through time seems to promise a whole new understanding of our reality. But time, as we know it, isn't a simple linear progression. It is, in fact, woven into the very fabric of the universe itself. Could there be a way to manipulate this fabric and travel to moments that lie beyond our present perception? And, if so, could the enigmatic and elusive wormhole provide the answer? A wormhole is a theoretical passage through space-time that could, in principle, connect two distant points in the universe, and possibly two different moments in time. It's like a tunnel that could bend the universe itself, shortening the distance between far-flung locations in space, or even between different moments of history. The concept of wormholes comes from Einstein's theory of general relativity, which fundamentally changed our understanding of gravity, space, and time. According to general relativity, space and time are part of a single continuum known as space-time, a four-dimensional fabric that can be warped and twisted by mass and energy. Picture this fabric stretched out like a giant sheet. The more massive an object is, the more it deforms the fabric around it. This is how we experience gravity. Now, imagine if that fabric could be folded onto itself. What if, instead of traveling through the vast expanse of space between distant stars, we could simply take a shortcut, bending space-time itself to form a direct link between 2 points? This is the essence of a wormhole. By creating a tunnel or a bridge between two regions of space-time, we could travel between them almost instantaneously, skipping over the space that normally separates them. But it's not just about space, it's about time too. If we could bend space-time in this way, could we travel through time itself? It's a fascinating thought, isn't it? Stepping through a doorway and emerging not just in another place, but in another time. Imagine walking out of a wormhole and into the distant past, perhaps witnessing the dinosaurs or even meeting your ancestors. Or imagine emerging in the far future, long after humanity has spread across the stars, seeing the evolution of Earth in ways we can't even begin to imagine. This is the tantalizing possibility wormholes present. But as we'll discover, even though wormholes sound like the perfect solution for time travel, they come with their own set of mind-bending complications and profound mysteries that challenge not just the laws of physics, but our very understanding of the nature of time itself. The mathematical groundwork for wormholes stems from the equations of Einstein's general relativity, which describes the gravitational forces exerted by mass and energy on the fabric of space-time. In simple terms, the more massive an object, the more it warps space-time. This means that, theoretically, if a massive enough object were placed in space, it could cause a fold in space-time that links distant regions of the universe. But there's a problem. This fold is not just a hole in space. It's a tear in space-time itself. What's more, this tear could connect not just different regions in space, but also different moments in time. One of the key theoretical models for a wormhole is the Einstein-Rosen bridge. In this model, a black hole at one end of the wormhole connects to a white hole at the other. A black hole is an area where gravity is so strong that nothing, not even light, can escape. A white hole, in contrast, is a hypothetical region where matter and energy are expelled. It's the inverse of a black hole. If such a bridge exists, one could, in theory, pass through it, emerging on the other side of space or, more fascinatingly, time. But to make this possible, we need a few things that our current understanding of physics has yet to provide. One of the most important of these requirements is exotic matter. In order to keep a wormhole stable and prevent it from collapsing under the immense gravitational forces at both ends, the wormhole would need a form of matter that has negative energy density, something radically different from what we encounter in our everyday experience. Exotic matter is not only theoretical, but it's also crucial for keeping a wormhole open long enough for anything to pass through. Without exotic matter, the wormhole would collapse too quickly, and any traveler attempting to cross it would be crushed under the immense forces involved. In fact, without exotic matter, even the very fabric of a wormhole might not survive. At best, a wormhole could exist as a fleeting, transient phenomenon, collapsing before it could ever be used for any meaningful travel. The implications of this are profound. Even if wormholes do exist, the odds of finding one that is stable enough for practical use are incredibly low. But perhaps the greatest challenge lies not in the wormhole itself, but in the paradoxes that time travel through a wormhole could introduce. This is where the fun and the confusion begins. Traveling through time presents problems that go far beyond just traveling between points in space. The most famous of these is the grandfather paradox. Imagine going back in time and stopping your grandfather from meeting your grandmother. This would prevent your parents from being born, which would prevent you from ever being born. But if you were never born, how could you have traveled back in time to prevent your grandfather from meeting your grandmother? The paradox creates a circular problem, a contradiction in which your actions in the past prevent the very event that would have enabled your time travel in the first place. To resolve such paradoxes, some physicists propose the many-worlds hypothesis, a theory suggesting that any change made in the past doesn't alter the original timeline, but instead creates an alternate one. This means that when you travel back in time and change something, you don't change your own history. Instead, you create a new branch of reality where events unfold differently. In this view, time travel doesn't disrupt the flow of causality, but instead creates multiple parallel realities. But this theory, like the concept of wormholes themselves, remains speculative, untested, unproven, and uncertain. Perhaps this branching of timelines isn't just an escape from paradoxes. It could also offer an entirely new perspective on how we understand reality. If time travel through wormholes leads to the creation of new timelines, then the very fabric of time becomes a vast network of possibilities. No longer is time an unalterable river, but rather a flowing sea of divergent paths, each moment spawning infinite futures and infinite pasts. Yet, even with these fascinating possibilities, the practical side of time travel remains elusive. And so, despite the rich theoretical foundations behind wormholes, we remain far from understanding whether time travel is truly possible. The quest to create a stable, traversable wormhole would require an enormous leap in both our understanding of physics and our technological capabilities. We would need to unlock the mysteries of exotic matter, understand the full nature of black holes and white holes, and solve the profound paradoxes that come with manipulating time itself. But the very idea of time travel is a testament to the human spirit, our unrelenting desire to explore, to understand, and to bend the rules of the universe. While the possibility of traveling through time with wormholes may remain out of reach for now, it serves as a reminder of how little we truly understand about the universe. Space and time are not the rigid, unchangeable structures we once thought. They are flexible, dynamic, and full of mysteries yet to be uncovered. Could time travel one day be within our grasp? We may not know the answer today, But the very pursuit of this knowledge keeps pushing us closer to understanding the very nature of time itself.